Collision theory, a more in-depth look. So in this video, we're going to review some of the things that we did in the way earlier podcast where we talked about a very brief introduction to collision theory. The main idea of that was just to get your mind working on this idea that molecules had to come in contact with each other in order to react. And that was useful for us when talking about rate laws. However, there's a lot more to say about this, and that's what we're going to do in this video. So first, we're going to go back and do a little bit of review in identifying what happens when a reaction occurs. And also, what has to happen in order to increase or decrease the rate of a reaction. And then we're going to add in some new things. So defining a transition state and activated complex, and determining how temperature has an effect on that. And then also determining if a reaction is endothermic or exothermic based on an energy level diagram. So collision theory says that if we want molecules to react, they have to collide with each other. So let's think about this in terms of rates of reaction. What has to happen if we're going to increase the number of collisions? If we increase the number of collisions, our reaction rate is going to have to increase because they're going to be running into each other more often. Now, this is generally what we want. So theoretically, we could say the reverse too. If we wanted to decrease the reaction rate, what would we do? And we could do that. But usually you want to increase the reaction. So let's think about it in terms of that. So if we want to increase the reaction rate, we need to increase the number of collisions. And there's two different ways that we can do this. One of the easiest ways to think about this is to think about people running around in a room and say, how would you increase their number of collisions? So one of the things that we could do is just increase the number of people. If I put 2 people in a living room or even a lecture hall, they're not going to collide with each other very often. There's going to be a very low rate of collisions. But now if I take that same living room and I put 15 people in it, there's going to be far more collisions. And so that, in this analogy, would just be increasing the number of particles. However many reactants you have, we can increase the concentration. And that's basically what we've been covering up until now. That's our reaction rate laws. But there's another way that we can do it too. And for that, let's use an analogy. Let's switch up analogy a little bit and instead think about, what if I put 2 baby sloths in a room? They'd be moving around. We could blindfold them so they're moving around randomly even. They're not going to collide very often. And that's just because they're moving so slow. Meanwhile, if you put the same number of people in a room and you blindfold them and you tell them to run really fast, you're going to get way more collisions. And when we think about that in terms, and we switch back and think about it in terms of molecules and atoms, we would want to increase their speed if we want to increase their rate of reaction. And if you think back to your previous classes where I know this has been covered, we can do this by increasing the temperature. So then there's one other thing we need to talk about here. And that's something called an activated complex or a transition state, and how that has to relate with activation energies. So if we have our 2 molecules and we let them collide, but they collide very slowly, or in other words, without a lot of energy, very often they'll simply bounce off each other and no reaction will actually take place. So nothing has actually been accomplished in that case. So you need something of sufficient energy to make that happen. You need them to collide with enough energy or enough speed that you're able to actually form your product. And this concept makes sense kind of in theory, that they may not react, but we want to put this in terms of energy and some definitions as well. So keep that idea in mind as we go about this next part. And let's think about why this is too. So these 2 collide to get some sort of product. Now, in that moment between when they're on their own and when they're in this new product, they're in what we call a transition state or an activated complex. This is not stable. This is a high energy state. It's not going to stay there for very long. So if you have really, really high-tech equipment and really, really high-tech research, there's people who can look at this. But it's generally not something that you're going to have in a beaker for very long. And so this is very high energy. So we can graph this, and we're going to look at these separately. So I decided to look at exothermic first. So this is an exothermic reaction. And you can look at this and you can see where your reactants start. So find A plus B on the graph. Those are your reactants. And if you trace the reaction progress, you can see that the first thing it does is go up in energy. And that peak of that energy peak is your transition state, or your activated complex. And it takes a certain amount of energy to get there. And if it doesn't get to that energy, then you're not going to have a reaction. Now, once you hit that energy peak, it's going to fall back down into its products. In this case, because I chose a exothermic reaction, it falls lower than the reactants. So now there's some values here that we want to pay attention to. First off, that difference between the reactants in the transition state. As you can see on the graph, we have that labeled EA. That's your activation energy, or the amount of energy that is required to start a reaction. Because that's the energy that you have to get those reactants to form that transition state to fall back down. Now, there's one other thing that we should discuss in here, and it's actually, you already have this from previous chapters, but if you look at the delta H. So just like before, the delta H is the difference between your reactants and your products. And in this case, it's an exothermic reaction. And so I have it drawn here, where you can see in between AB and CD. And that is your delta H. So nothing really new there, but I want to point it out on this graph since you haven't seen it in this graph before. Now let's look at the exact same thing, but for an endothermic reaction. And you may actually pause the video here and see if you can draw the graph for an endothermic reaction before I show you. Because we know from earlier classes the difference between exothermic and endothermic. Exothermic releases energy, endothermic takes energy in. So take a moment and see if you can draw that before moving on. So let's look at the graph now. It looks almost the same as before, except that now your EA is still going from AB up to your transition state. But if you look at your relationship between CD and AB, you can see that your products are higher. Your products are higher than your reactants. And so your delta H is therefore different because of that. Now, the focus, of course, of this chapter is on the kinetics, and so we want to look at that activation energy. We see here that it takes energy to go up to reach that point. And just like for the exothermic one, it then can fall back down. So your transition state or your activated complex is your high energy point. It's that point where it's not really the reactants and it's not really the products. It's just this unstable transition state. So this was a very conceptual video, so let's just quick review all the main points. For a reaction to occur, atoms and molecules must collide. If you increase either your temperature or your concentration, you'll generally increase your reaction rate. A transition state, or an activated complex, is a high energy state that the molecules must pass through between your reactants and your products. We didn't talk about it here, but I should mention that you can have 2 or 3 transition states in a reaction. So you'll often see a kind of energy diagram that looks like this, and that's okay. There's some of those in your book that you can look at if you want. In exothermic reactions, reactants will be higher in energy than their products. And endothermic reactions, reactants on the other hand, is going to be of lower energy